Hello, everyone. I'm Lisa Broderick, and it is a chilly afternoon here in Florida. It is 65 degrees. We hope it warms up to the regular 80s. Of course, that's why I live here rather than in the Northeast, where I lived for so many years. But we left off last time with a brand new science called quantum physics, which came out of a problem that when scientists tried to apply the classical laws of physics to explain how the smallest possible bits of matter and energy behave, they simply couldn't explain it. And specifically, when they tried to measure these tiny particles, the problem called the measurement problem, we talked about that last time. Today, that same measurement problem is at the core of the debate going on in quantum physics. The reason is that the measurement problem is such an issue is this. Scientific experiments conducted over the last 50 years or so have come to suggest a highly controversial view. This view holds that by the simple act of a human being looking at something, in physics called observing, we humans actually change what we are looking at. And the way we do this is through our thoughts. That would cause the definition of quantum to include the ability to change the behavior of atoms through thought. Wow. Well, at the first, this seemed so crazy that scientists couldn't believe it to be true. And so experiments and theories were developed to try to disprove the conclusion. None were able to do so. And so quantum physics models the smallest components that make up our world. The particles of energy and matter, which scientists study, are so small that they can't even be seen, of course. And stranger than that, sometimes they aren't even particles, but they are waves. They're not even waves as we know them. They are called, among other things, probability waves, which would mean that they only have a probability of existing. Oh, and one more thing, because they haven't been observed, they haven't even happened yet. And so you can appreciate why modern science has a problem. So going back to the time before quantum science, in the 1900s, physicists were stumped by something called the photoelectric effect. And that's really just a way of saying that metal reacts in weird ways to electrons on its surface. Now, Einstein realized that if a certain frequency of light existed as discrete packets of energy, like we think of particles as being, this might explain the problem in the photoelectric effect. But later, Robert Millikan won the Nobel Prize for proving that light is in fact a particle, implying that waves and particles are mutually exclusive. Now, hold this thought in your mind because it's going to be important later. Because the Danish physicist Niels Bohr took that idea and then somehow matter had qualities of both waves and particles. So in 1929, Bohr and his fellow physicist Werner Heisenberg developed the first theory of what quantum physics calls the Copenhagen interpretation of quantum mechanics. The Copenhagen interpretation says that physical systems generally do not have definite properties prior to being measured, observed. And to prove it, they performed something called the double slit experiment, one of the most famous experiments in quantum science. Now, don't cringe. We are going to talk about a scientific experiment here, but I promise you it will be fun and interesting. So the double slit experiment studied particles of light called photons. We all know that. After they traveled from a light source to hit a photographic plate. Now, a screen was placed in between the light source, and it had a single slit cut through the screen. Photons were emitted from the source, kind of like shooting a light out of a gun. And as a result, a fuzzy image was created by the photons that went through the slit in the screen that hit the plate behind it. So now this is what the single slit experiment looks like. So here we have, hold this up, right? We have the light source, these are photons, and this is the barrier, right? There's one slit here, they go do-do-do-do-do, and they go through and they hit the photographic plate. This is them on the photographic plate. And they were doing this because photons should behave in a very specific way when they hit that photographic plate. But, and they did, they actually met the scientists' idea of what would happen in that case. But not satisfied with that result, these early pioneers experimented with what might happen if they got two slits in the screen. Now remember, they were trying to figure out what photons would do that they assumed to be solid particles when they hit the metal behind it, the photoelectric plate, back to the photoelectric effect. And so you would think that single photons would go through just one slit, or you might think that they would go two images going to two slits, but they didn't get either of those. And so this is the famed double slit experiment, okay? So now we have photons here. And the photons are going through not one, but two slits, right? And they go here. Oh, is this upside down? Well, you could see it anyway. So here's photons, right? They're being shot, They go through two slits, and they make patterns here on this electric plate, this photoelectric plate, this metal source. Remember that photoelectric effect. And they're making the patterns as they hit the plate behind it. But what happened was very disturbing and interesting to scientists, because instead, light appeared to pass through both slits and not end up on either side looking like a photon particle. Instead, it ended up looking like waves. Now, this was the debate between photon particles and waves that we talked about before. It ended up like looking two separate waves that produced a certain type of pattern on the photographic plate. And this is consistent with a pattern that's created when waves collide with one another. So things that are waves interfere with one another, as it's called in science. Like when you throw two rocks into a pond simultaneously at different locations, you'll see the rings moving away from the points of impact that resemble either troughs, low points in the water, or crests. An interference pattern, as it's called by scientists, occurs when the rings from two rocks collide. And so now let's take a look at rocks on a pond. So these are rocks thrown onto the pond, and they create waves. Everyone's seen this, right? This is an interference pattern. This is what happens when the waves interfere with one another as the rocks are being thrown in and disturbing the surface of the water, just like the photographic plate. Notice there's a pattern here. And this is, in science, this is called the interference pattern. So this is a more scientific way of looking at it when the waves collide, okay? And so two crests hitting each other, they would have 4 times the height, and two crests that are different would subtract from one another from trough sizes. That's just sort of mathematics. But the real interesting point was that completely different from waves, classical, meaning non-quantum particles, don't exhibit interference. They behave like bullets shot out of a machine gun. And so fired at a target, they just add up. Now, firing 2 machine guns at targets near each other will get 2 big piles of bullets. But for some reason, when light is used, the light shining from a single source against the barrier with the 2 holes, the slits in the double slit experiment, will result in bright bands and dark bands on the screen behind the barrier. And since waves and particles were mutually exclusive to one another, this experiment should have settled the debate of light for all time, but it didn't. Because remember, in the double slit experiment, we got piles of bullets. We did. And so this was the issue. So what was the difference when they hit the plate behind the screen? Here's what happened when they did that. Each photon behaved as though it had gone through just one of the slits. The wave pattern on the photoelectric plate disappeared, and they got what they expected, photons that looked like photons instead of waves on the other side of the slit. But when they didn't observe, as strange as it may have been, this was only when the photon was observed as going through one slit or the other that its behavior went from that of a wave to definitely that of a particle. So are you following this? When they saw something, it looked like a solid particle when they observed it. When they didn't, then it was a wave, as though it had happened in nature, 2 waves colliding, like the rocks on the pond. So in case you think these results are simply due to how weird light is, that same double slit experiment has performed with other subatomic particles, such as electrons. In fact, experiments have been done with everything from neutrons to atoms to even larger molecules. These results can no longer be laughed off as being due to the weirdness of light, like the first experiments. Instead, these are actual particles that make up our material world, our solid daily reality. These particles have also been proven to also act like waves going in 2 places at once when it's unobserved, and assembling itself into a single particle when it's being observed. Now, I know it's a lot to follow, but let's fast forward to the present time. So recently, some scientists tried to isolate the source of the effect. Why is it when something is observed that it becomes solid, and when it's not observed, it's a wave? And so what they did was, in which one outcome occurs when a human being is doing the observing, and another outcome happens when the experiment is unobserved. Scientists realized that random number generators could be used in the place of photons in order to determine whether the human thinking about them has affected certain outcomes. So it works like this. Scientists created a device that was meant to produce entirely random flashes of light, with each flash being either green or red. And then using probabilities, there was a 50-50 chance that any flash might be one or the other. Then scientists set up people who were supposed to use their minds to try to change the flashes to one color or another. But the results surprised even the parapsychologists, as well as some physicists, because a statistically large amount of data showed that the humans were able to change the flashes from one color to another so that the flashes were no longer random. Now think about that. And then a scientist took that one step further. One researcher named Helmut Schmidt decided he would also test the impact of time in his own experiment. So he performed the same experiment and recorded it on an entirely random data on a floppy disk. Remember those? So much later, he played back the already recorded random data to a human subject, who again was supposed to change the flashes to either red or green by using the power of thought. He found that the same result occurred as in the prior experiments. The human subject seemed to cause the results to be not random, even though time had passed, and the results should have been random. So here's what happened. The random flashes were recorded on a medium, an electronic medium, and then time passed, years passed, and years later, someone thought about it and changed it from random to non-random. And so whether the recording was changed by human thinking about it after the fact, no one knows, but it suggests that somehow the unobserved past hasn't happened yet. So here is the key takeaway behind quantum science. Schmidt and many others uncovered what is called the observer effect and the collapse of the wave function. What this means is, since waves behave like particles when they were observed in those early experiments, scientists came up with the phrase the collapse of the wave function, which implies that the wave collapsed into a particle. It became a particle. But what is really meant by this phrase is that nothing exists until we pay attention to it. Here, the we is what science calls the observer. So the observer effect simply means that humans are paying attention to something. And when we do, then it collapses into that which we experience as reality. And so with that, I'll let you ponder the nature of what is really going on in your daily life. Oh, that's Al. Say hi, Al. And I'll leave you to being here in the now.